Hi everyone, and welcome back from the lunch break, and I hope everyone is refreshed. And so let's begin the afternoon session on security of post-quantum signature. The first paper of this section is titled Thorough Power Analysis on Falcon Gaussian Samplers and Practical Countermeasure. And because none of the authors could attend the conference, so Hao Xianglin will be presenting the paper on behalf of them. Okay, please.
Thanks for the introduction. I'm the proxy speaker of this talk. This is work given by Xiu Han, Shiduo, Yang, Weijia, Qidi, Ximing, and Xiaoyun. This work mainly focuses on the side-channel attacks of the Falcon. It first further refines the key recovery of the Eurocrypt work in 2023. The required traces can be reduced to 85%. Furthermore, it gives a complete power analysis for half-Gaussian leakage and sign leakage is existing in Falcon's integral Gaussian sampler, and then proposes effective and easy to implement countermeasures against the both leakage. So let's start from some background knowledge. The first one is the introduction of the Falcon. And Falcon is one of the three post-quantum signature schemes selected by NIST for standardization. It has competitive overall performance and especially the smallest communication cost among all other three selected signatures. So Falcon is a lattice-based hash and sign signature scheme. It utilizes a paradigm from GPV8. The evaluation of this construction mainly involves some earlier constructions like GGH, N-true sign, and the provably secure framework GPV, and the advanced NIST standardization Falcon. In early constructions, the signing uses a deterministic algorithm to find the closed vector. So the distribution of the signature leaks the information of the basis B, which is quite insecure. And I think in 2006, Ruan and Reggae found an attack to this sort of signature. So in GPV8, the authors proposed a provably secure hash and sign framework, and the signing uses lattice Gaussian sampling to prevent the secret leakage. So in the Falcon, it is originally based on the GPV scheme, and then it is initiated over N-true lattices and explores some techniques like the fast Fourier Gaussian sampler, which makes the sampling run in quasi-linear time. So next, we mainly depict the Gaussian sampler in Falcon. You can see that in the left layer, FFO sampler is a ring-efficient variance of Kellin GPV sampler. The lattice Gaussian sampling are reduced to a series of one-dimensional integral Gaussian samplers with different centers and standard deviations. If you are familiar with the GPV scheme, this is actually similar to it. And in the middle layer, the sample Z is one-dimensional integral Gaussian sampler. It first samples Z plus from half-Gaussian distribution by calling the subroutine base sampler, which is in the right layer. And it computes Z by using the sign bit B and then computes S to perform the rejection sampling to obtain the target distribution with certain probability. So what is half Gaussian? You just eliminate all the negative part and concentrate on the positive part and including zero. So for the base sampler, it is implemented with table-based approach. So next, we briefly recall two leakages existing in Falcon's Gaussian sampler. The first one is the Gaussian half leakage, which is identified in base sampler. So one can classify if C star equals to 0 or not by simply power analysis against the comparison in the step 4. And the second one is the sign leakage. One can determine the sign bit B by template attacks against the sampling B, computations Z and X. And in this work, we further improve the key recovery of our Eurocrypt work. So let's talk about the further improvements of the Eurocrypt work. Due to the intrue simplicity, 4 rows of Falcon key satisfy the following relations like this. Compared with the Eurocrypt work, one trace can contribute more information, and then one can further refine the learning with intrue simplicity. And using the learning technique, one can obtain the approximation of secret key. So we further correct the errors from the approximation by using probability-based pressed decoding method. So in this work, by thoroughly exploiting the half Gaussian leakage, 27,500 traces are sufficient for full key recovery with good probability. Using thoroughly sign leakage, 25,000 traces are sufficient for full key recovery with good probability. When the attacks use both leakage, one can mount exact key recovery with 6,500 traces. So compared with the Eurocrypt work, our method significantly lowers the cost of key recovery attacks. The required traces are reduced by at least 85%. Next, we give the complete power analysis of half Gaussian leakage and sign leakage. More precisely, we identify new sources of these two power leakages existing in sampler Z and perform security evaluations on more universal platform chip whisper. For half Gaussian leakage, the original sources identified in the chess work are marked in red color, and the new sources for this work are marked in the orange color. Concurrently, we identify half Gaussian leakage from the new sources, including the computation ZX, rejection sampling, and return operation. So we perform the complete power analysis by integrating original and new sources. And we report the classification accuracy for half Gaussian leakage. As we can see, the leakages from new sources can also achieve higher accuracy. For sign leakage, we identify the new sources of this kind of leakage, including the rejection sampling and return operation. So we also provide a complete power analysis by combining original and new sources. And we exhibit the classification accuracy for sign leakage. And we can see the leakages from new sources can also achieve sufficiently high accuracy. And finally, we propose an effective and easy to implement countermeasures against both half Gaussian leakage and sign leakage. For the half Gaussian leakage, Chesswork proposed a simple trick to mitigate this kind of leakage. They encoded the sign bits with the binary bit instead of 0 to 255. However, we validate their tricks on Chip Whisperer, and the classification accuracy is still at least 97%. For our countermeasures, we first encode the sign bits with 1, 2 to eliminate the Hamming weight difference. Perform multiple sampling to average half Gaussian leakage, and then compute all intermediate values by traversing all possible values of Z plus, and finally return the value with the index Z star, Z plus. Then we perform security evaluations against the half Gaussian leakage for our countermeasures. The classification accuracy for half Gaussian leakage is at most 58% with different sources of leakage. As shown in Eurocrypt work, when the accuracy is less than or equal to 65%, the required traces for full key recovery are much more than 10 million, and these attacks become impractical. And for the sign leakage, Eurocrypt work encoded the sign bit with the set 1, 2 instead of the set 0, 1 to mitigate this kind of leakage. However, we also validate their tricks on Chip Whisperer, and the classification accuracy for the computation of X is still 75%. For our countermeasures, we further compute all intermediate values by traversing all possible values of B prime, and finally return the value with the index B prime. Next, we perform security evaluations against sign leakage for our countermeasures. The classification accuracy for sign leakage is at most 62% with different sources of leakages. As mentioned in the Eurocrypt work, these attacks using sign leakages also become impractical. And we also report benchmarks for Falcon signing with countermeasures. The overhead on the signing speed of our countermeasures is about 3.5 times. The above evaluations shows that our countermeasures admit a practical trade-off between the efficiency and the side channel security. And finally, in conclusion, this work gives the complete power analysis of the Falcon's integer Gaussian sampler from the perspective of attacks and protections. And our source code is available at this GitHub link. So with the deployment underway, the side channel security of post-quantum schemes requires more investigations. And I'm grateful for your attention. Thank you.
Thanks for the presentation. So we have 5 minutes for questions. Okay, yes, because this is a proxy presentation, so if you have any question, please drop an email to the authors. Yes, thanks.
Thank you.
Sorry. So the second paper is titled Finding a Polytope, a Practical Foe Attack Against Dilithium, which will be presented by Paco Azevedo Oliveira. Yes, please.
Okay, so thank you everyone. My name is Paco Azevedo Oliveira, and today I will present to you a fault attack against dilithium. That is a joint work with Anderson Caliviera, Benoît Cogliati, and Louis Goubin. So, rapidly, I will start by explaining the main takeaway of our paper. Then I will briefly explain the context of our work, the details behind dilithium, our attack method, and the practical results we have obtained. So, as you may know, dilithium is a signature algorithm that has been recently standardized by the NIST and which use rejection sampling. In our paper, we study what happens if an attacker, for example by doing physical attacks, can recover signatures of dilithium that should have been rejected. We show that the security of dilithium completely collapses as soon as we remove one of the two testes in dilithium. And so, from our paper, we see that this type of attacks is practical in a side channel setting, and therefore it is necessary for implementation of dilithium to protect not only the value manipulated during the rejection test, but also the test itself. And also something that is important, at least it is for us, it is that the code is publicly available on the GitHub of Anderson, and therefore you can try to redo the attack yourself or try to see if your protected implementation resists to this kind of attacks. So, as I explained, dilithium was recently standardized by the NIST, and it is recommended as a main standard, and so dilithium will be used in most cases to sign digital signatures. And this use case could include use cases where side channel attack and fault attacks are possible threats, and therefore the security of embedded implementation of dilithium need to be carefully assessed. Now I will quickly explain how dilithium works. So for the key generation, it is a simple MLWE instance. Alice draw two small polynomials, S1 and S2 at random, calculates A times S1 plus S2. The public key will be the matrix A and the vector T, while the secret key will be the knowledge of the two secret polynomials S1 and S2. In addition to this, dilithium will use two algorithms that can decompose integer into high parts and low parts, which I will call high bits and low bits, and by simply doing the Euclidean division. And of course, if one can do it with integer, one can do it with polynomials and vector of polynomials. So I will continue noting high bits and low bits for a polynomial or a vector of polynomial by just taking the high bits or low bits of each of its coefficients. Now, for signing messages, so as you may know, dilithium follow what we call the Fiat-Shamir-Wizard paradigm. So Alice will start by drawing a random polynomial vector. From this random polynomial and the message, she will create a challenge, and she will use the secret key, the knowledge of S1, to provide a response to this challenge, named Z. So the response Z verifies this following equation that is the most important in dilithium because it makes a link between the public key and the signature and the secret key and the nonce. Because the signature will be C, the challenge, and Z, the response. Unfortunately, we cannot directly output Z because we have to impose two conditions. The first one is an upper bound on the coefficient of Z to avoid any secret key dependency, while the second one, well, it's not directly this one, but I simplify it a little bit. It is to answer both security and verification. So at the end, if we choose the nonce and Z correctly, we will have the following inequality. The inequality on the left being by pure definition of Z, while the equality on the right will be by rejection. So we draw a response Z, which verifies this equation, and we use the rejection to choose a correct nonce, which verifies this inequation. Then for Bob to verify the signature, what Bob will do is that he will recompute the challenge by calculating the high bits of AZ minus CT that are the same than those of high bits of AY. And then he will verify that the response to the challenge, Z, verify the bond imposed during the signature time. So, unfortunately, dilithium is not as simple as I explained, because the public key is actually compressed. The vector T in itself is not completely known to the verifier, but only its high parts, T1, while T0, the low parts of T, is placed in the secret key. And therefore, the verification I presented is not completely possible, because Bob don't know T0, and therefore he cannot recompute the high bits of AZ minus CT. So the authors of dilithium come up with two algorithms, named make hint and use hint, to allow Bob to recompute the high bits of AZ minus CT, even if he doesn't know T0. So in the real dilithium, as I said, only T1 is part of the public key, while T0 is placed in the secret key. At the signing time, Alice had to add few hint vectors, in addition to C and Z in the signature. And at the verification time, Bob will use the hint provided by Alice to recompute the correct value of high bits of AZ minus CT. Okay. In the paper, what we study was the removal of the two tests in the rejection sampling, but in the presentation, I will only focus on the removal of the second test. Anyway, the ideas are completely the same, and it is studied fully in the paper. So, if we study an algorithm named fsig for faulty signature, since we have removed the second condition, from time to time, some signature won't be accepted by the verification algorithm because the high bits of AY minus CS2 may differ from those of AY. If it is the case, the signature won't be accepted because Bob won't be able to recompute correctly high bits of AY. What we show in the paper is that these two polynomials of vectors, W1 and W1 prime, are almost the same because they are at most one coefficient that is different, and this coefficient will always be +1 or -1. And we have a proposition that states that if this assumption is correct, then Bob can recompute the correct W1 that was used at signature time. And to do this, the proof is simple. Bob only has to use the fact that the challenge C was derived from the message and W1, and so he can carry out an exhaustive research on the coefficient of W1 prime and hash it with the message. If he succeeds in finding C, then he has recovered the correct W1. A quick remark is that even if the assumption 1 is not verified, then we can simply discard the signature and we proceed with another one. Okay, so finally, this is perhaps the most important slide of the presentation. We show that each signature of a faulty SIG that won't be accepted by the verification algorithm will provide an inequality on the coefficient of the secret key. So the proof can be summed with this drawing. If I know that the high bits of AY minus CS2 are less than those of the high bits of AY, this means that the quantity CS2 is too big in a certain way. So CS2 is positive and is either bigger than a certain bound that I can calculate using known parameters and the public key. So if I present this toy example where I assume that I know all the key coefficients apart from the first three, I will sign messages with my secret key that I don't know. And from time to time, I will have inequalities that are verified by the three coefficients that I don't know. And originally, I search for a point into the cube. And by signing messages, I will narrow the set of possible solutions to the set of inequation. And so this type of a set of solution to inequalities is often called a polytope. And therefore, what we are seeking for is a point in a polytope defined by a set of inequations. So it is very natural that we use linear programming methods. We will use it in two different ways. The first way is to upper bound the number of solutions to the set of inequations we have collected. By minimizing and maximizing all the coordinate functions, we can have an upper bound on the number of points in our polytopes. And if we manage to collect sufficiently many inequations for S2 to be the only solution, all we have to do is to minimize or maximize any function. And so our helper method will give us a point that verifies all the inequations. Since we know that S2 is the only solution, we will recover the secret key. So in practice, this is exactly what we have done. We estimated, using statistics for a large number of keys, how many inequations we have to collect for S2 to be the only solution. And we stated that around 11,000 inequations should be enough for S2 to be the only solution. So we tested our attack methodology for 100 keys of dilithium. Each time we collected around 1.5 million signatures, which lead to an average of 11,000 inequalities, and we managed to recover 99 out of the 100 keys of dilithium. For the miss key, it was due to a solver timeout, and we removed the solver time limit, and in a little less than 1 hour, we finally recovered the only missed key. And so, conclusion, like I said, this attack illustrates the power of LP method because we are searching for a point into a cube minus 2, 2 in dimension 256, and we found it every time in under 1 hour of calculus. And again, this implies that if you have an implementation of dilithium that can be attacked by side channel attacks, then the test must be protected against false attack. So finally, some hidden problem that I didn't talk during the presentation. What I presented was using the specification of dilithium, which is not directly followed by the dilithium reference implementation, because this specification makes two calls to the decompose function, which is the function that allows to use Euclidean division. And the authors of dilithium show a way that this can be avoided at the cost of storing W0 in memory. So in this equivalent version of dilithium that I named SIGREF for signature reference implementation, we keep in memory W0, and the authors of dilithium explain how to do equivalent tests in the rejection sampling, but without using 2 times the decompose function. This version, that is equivalent to the SIG specification, is 2 to 5 times more faster, and therefore any implementation on a constrained device will use this implementation. And so what we show, and to our knowledge, this is the first result that shows something like this, is that these two implementations are no longer equivalent in a fault framework. If we remove the second test of these two implementations, they do not behave the same way at all. So for specification, as I explained, from time to time, some signature won't be accepted by the verification algorithm. And when it is the case, I collect inequalities. I collect sufficiently inequalities for having an only solution. And then it can solve for retrieving S2. However, for the implementation of dilithium, where I remove the second test, all the signatures produced by this faulty reference implementation of dilithium will pass the verification algorithm. And therefore, to find inequation on the secret key, we have to perform the real verification of dilithium, those the one that use the knowledge of T0. And so, by performing this alternative verification of dilithium, we end up with the same type of inequalities, and we can solve in the same way. We collect sufficiently many inequations to have only one solution, etc., and we find the secret key. So, finally, a second conclusion that perhaps is more important than the first one is that we show that the two verification algorithms of dilithium are no longer equivalent in a fault framework, because if I take the dilithium reference implementation and that I remove the second test, it will produce incorrect signature that leaks part of the secret key, and that will be accepted by the verification algorithm, reference verification algorithm of Dilithium. And this, in particular, implies that you cannot secure your implementation by just doing a verification before outputting the signature, because you will have incorrect signature that leak information about the secret key, but that will be considered valid by the Dilithium reference implementation. Thank you very much.
Thanks for the presentation. So we have plenty of time for questions.
Thank you very much. So in your attack, you had a success probability, and I was wondering where that comes from. You used LP, and then you round to the next integer. Is that
Yes.
where it comes from?
Yes, yes.
And then you round incorrectly, and then.
So in the two cases, for the first, so for specification, we had one missed key, but it was because we set a timeout to the solver. So we said if after half hour of calculus we don't find anything, we just say the key is 0 and.
So, but what is the timeout? It's super efficient, right? It's like 3 minutes average.
So we have how to say.
It's not that
huge
you round
variation.
It's not that you round incorrectly. It's like a Las
No,
Vegas algorithm, so it just times out and then you
the
say
solver
it's
times
failed.
out. Yes. And for the implementation, the two missed key, it was the same problem. And so after 1 or 2 hours of calculation, we managed to recover the missed key.
Okay. There can be instances where it runs very long. But
Yes.
this is rare.
So we decided to use LPsolve, which is a kind of hold LP solver. So this result could be improved by using a more powerful solver like Gurobi or stuff like this.
And you never output a wrong key, right? Because you check.
No, so we did some tests, but for the final, for this final result, no, we always had the correct key.
Okay, thank you very much. Very nice.
So regarding the faults, so do you have to fault every single signature that so because there's like 1,250,000 signatures, so every single time you have to make that fault, right?
So we wanted to do the paper as theoretical as possible, to not attack only one implementation of Dilithium, but to show how could it be possible. So actually, I'm not an expert into fault injection. I said that it will depend how the test is made. If you succeed into, I would say, invasive fault, then you only have to do it once. But yes, maybe you will have more information on the thesis of Anderson Caleviera, because it is he did his thesis partly on this. So,
and could there be like trade-offs in some sense where you observe less signatures, but then the success probability is not close to 1, but still like significant?
Yes. So the problem about this is that it's very difficult to have an intuition on how the polytope looks. And so if you have slightly less in equation, for me there is a high chance that you cannot just carry an exhaustive research. Because you could do something like this, so you can upper bound the number of solutions of your polytopes, and then just try each possible value. So this will be a possible trade-off, but you will have to solve way many LP problems, because 2 for each coordinates, and therefore it will be way heavier in terms of calcul.
But you have like integer solutions, right? So you might...
No, we cannot really use IP, integer programming, because this is way more complicated than just LP programming.
Yeah.
So what we want to do is that the polytope is very narrow, 0, just the secret key, and then we use LP, and we will get an integer solution.
Okay, thank you.
I'm going to ask you about the countermeasure for this attack. If I understand correctly, if you use the imperfect verification algorithm written in the FIPS, you can prevent the leakage of the information of the secret key. Is it correct?
Yes. So, so what we show is that the complete verification with the knowledge of T0 will detect the incorrect signature, whereas the partial verification, that is the standard one, will not. But it depends on how version you use on Dilithium, because if you do not inject any faults, these two versions are equivalent.
Okay.
But if you take the specification, then this verification is less powerful. So it depends on how you implement Dilithium.
Okay, thank you. One more question. Do you think another attack, fault rejection attack, that that can be succeeded even with the verification before the out of the signature?
So if I think there could be an attack, but this type of attack is an example.
Okay.
So yeah.
Okay.
And it's quite dangerous because most of the company do stuff like this. They just do verification afterward and they protect this verification.
Okay.
And so this is very dangerous.
Okay, thank you.
Okay, so let's thank the speaker again. And let's move on to the third paper. The third paper is titled One Bit to Rule Them All, Imperfect Randomness Harms Lattice Signatures, which will be presented by Nicolas Kraus from Home University Bochum. And please.
Thanks for the introduction. The paper is a joint work with Simon Damm, Alexander May, Julian Nowakowski, and Jonas Tietke, all from Bochum. As you all will know, NIST is in the process of standardizing signature schemes. Recently, a new lattice signature standard has emerged, MLDSA, which was also known as dilithium. MLDSA is built using the Fiat-Shamir with aborts technique. It uses many optimizations like module lattices, but in its essence, it works over the integers and with integer vectors. We will abstract the optimizations away and consider the problem of secret key recovery. So the secret key consists in two integer vectors, S1 and S2, and the public key takes some public A and computes the inner product with the secret key S1 and adds one value, one entry of the secret key S2, and reduces everything modulo Q to yield the T. And these public key equations, they are learning with errors, LWE equations. So to recover the secret key from the public key, one must solve the believed to be hard problem, LWE. Let's have a look at secret key recovery from signatures. So a message is first hashed to some challenge vector Z, and then the inner product of the challenge with the secret key S1 is summed with a random value to yield the signature Z. Now there is no reduction modulo Q, so in general, this LWE without reduction modulo Q, which is also called integer LWE, is an easy problem, but a step called rejection sampling ensures the zero knowledge property. So for any number of signatures, it is not possible to recover the secret key because of the zero knowledge property. But we asked ourselves, well, what about side channel attacks? Is there a possibility to gain some side channel information to recover the secret key from signatures? In 2020, Liu, Su, Sun, Zeng, Bang, and Bing had the idea to break the zero knowledge property via a leak bit. They proposed an attack that uses a single leak bit in the random value to recover the secret key. And the attack setting is as follows. So we assume an oracle that gives signatures. The signatures are correctly computed. Rejection sampling is applied. And then a single leak bit, a single bit of the random value is given to the attacker. Say the random value is in the range plus minus 2 to the 17. Then it has 18 bits in binary representation. And one of these 18 bits is known to the attacker at an index equal to or larger than 6. The attack then proceeds to extract integer LWE samples, that are essentially the signatures with a shortened random value. So the leak bit is used to shorten the random value to the range plus minus 2 to the j. And then the key is recovered via linear regression and rounding, which is a technique to solve integer LWE proposed by Bootle, Delaplace, Espito, Fouque, and Tibucci. So how many signatures do they require for the key recovery? On the x-axis, you can see the leakage index j, and on the y-axis, the number of signatures for successful recovery in a logarithmic scale. And you can see that for every increment of the leakage index, the number of signature quadruples. It increases fourfold. And because of that, the attack becomes inapplicable, infeasible for the higher order leakage indices because of the space requirement. The 2 to the 30 or 2 to the 40 signatures that must be stored and processed with linear regression are not achievable in the expensive working memory RAM, and so the attack becomes infeasible. We asked ourselves how to improve the attack. Is it possible to reduce the number of signatures? Can we achieve the higher order leakage indices? Before I come to our results, I want to emphasize the leakage model. So per signature, C is one single bit leaked of the random value. And when I say leakage index, I mean the bit index of the leaked bit in the random value. So let's proceed with our results. In short, we enable the attack for all higher order leakage indices. First, we analyzed the sample extraction using the leak bit, and we found that it does not always break zero knowledge. In fact, it does not, especially for the higher order leakage indices. Most of the times, zero knowledge is not broken. With this novel insight, we could improve the sample extraction and eventually make the attack independent of the leakage index, and by this enable the attack for all higher order indices. Also, in the paper, we estimate the number of samples and give a lower bound for the required number of samples. Before I go on with our improvements, I want you to gain an intuition for rejection sampling and why it is needed. So assume we are in the MLDSA signature creation phase, and you get a signature candidate C, which consists of the inner product that contains the secret plus some random value, and you know by specification that the inner product is bound by some value beta and the random value bound by some 2 to the 17. And you can see the distribution below. On the x-axis you have some value, and on the y-axis the probability that the signature candidate has this value. And now assume you are given the maximum possible, the largest signature candidate value, which is 2 to the 17 plus beta. You would instantly learn that the inner product that contains the secret must have its maximum value beta, simply because there's no other combination possible than the maximum random value plus the maximum inner product value. We can play this game on and on. Assume you get the second largest signature candidate value, then there's two possible combinations, either the second largest random value and the largest inner product value, or the other way around. In any case, you learn that the inner product value has at least its second largest value. We can play this game on and on. Of course, we lose information with every decrement until eventually we reach some threshold, 2 to the 17 minus beta, where we learn only that the inner product value is larger than minus beta, which is an empty statement. It's vacuous because we already know it by specification. So this is exactly the threshold where rejection sampling comes into place. You can see in blue depicted the part of zero knowledge samples, and in red depicted the informative samples, and the rejection sampling step simply cuts off the informative part because they contain information about the secret, and all the resulting signatures, they can be given out by MLDSA. They are all zero knowledge. Please notice that the threshold for the rejection depends on the random value. So assume we are given a random value range 2 to the 10 instead of 2 to the 17, then of course everything above 2 to the 10 minus beta would have to be rejected. Now keep this in mind when we analyze the sample extraction. On top, you can see the distribution of the lithium signatures after rejection sampling. All of them are zero knowledge, but then the attacker is given one bit of the random value, and he uses this bit to shorten the random value to the range plus minus 2 to the j. And the resulting distribution, the resulting situation is essentially the same like before rejection sampling, just with a narrower, a shorter range of the zero knowledge samples. But essentially the informative tails, they are back, and we are back to the easy problem. There's a problem with it though. For every increment of the leakage index, the range of the random value doubles, and thus the range for the zero knowledge samples doubles. And this happens for every increment of the leakage index. So for the higher order leakage indices, the share of zero knowledge samples becomes larger and larger, and the share of informative samples, it diminishes, becomes smaller. So now we can intuitively see why the attack becomes inapplicable for the higher order leakage indices. There's only a really small share of informative samples, and the majority is zero knowledge. They are not cut off. They all must be stored and processed, and so the attack is inapplicable. But if we want to remove the space requirement to improve the attack, we could simply get rid of the zero knowledge samples, because independent of the leakage index, we had the red informative tails. So this is exactly what we did. We achieve independence of the leakage index by two steps. First, we use only informative samples from the tails. That is, we apply a threshold and cut off all the zero knowledge samples, which is the opposite what was done in MLDSA, because we are now in the attacking perspective. We drop all the zero knowledge samples and keep the informative ones. And in a second step, we center the informative samples, and we result in a distribution that is independent of the leakage index, and the random value, which acts as error in the equation, is in the range plus minus beta. Now beta is independent of the leakage index. It depends only on the parameter setting. And let's put everything together. So the aim of our algorithm is to recover the secret key. As input, we are given an oracle that gives us signatures, the public challenge, together with a single bit of the random value. In practice, of course, you would not use an oracle, but get many signatures. And the algorithm enters a loop. First, we obtain one of the signatures with the leak bit. Then we use the leak bit to shorten the random value. And we do this until we get something that is informative. So one signature yields one sample, but these samples are either zero knowledge, the blue part, or they are informative. If they are zero knowledge, they are dropped, and we take a new signature until we get informative ones. And then we apply the centering, the independence transformation to achieve independence of the leakage index. And we do this until we have sufficiently many samples collected. And finally, we estimate the secret key over the reals using linear regression and round it. In our paper, we give an estimation for the interested, how many signatures are required for the attack to recover the key successfully. Let's look at the results. So on the x-axis, you can see the leakage index. On the y-axis, the number of informative samples in million. You can see that, for example, for MLDSA 4.4, we require 500,000 informative samples, independent of the leakage index. For all higher order leakage indices, we require the same number. For MLDSA 6.5, we require more, 2.5 million. This is because the value beta is larger in MLDSA 6.5, and thus the informative samples are a bit less informative, and we require more of them to recover the secret key. But of course, for the attacker, it is much more important how many signatures does she need. And you can see on this slide that the number of required signatures, it doubles with every increment of the leakage index. But this is because the number of zero knowledge samples doubles with every increment. And the best we can do, of course, with zero knowledge samples is discard them. So this doubling is inherent, optimal to the attack. You can imagine that the attacker, for any of the leakage indices, she waits until she has 500,000 informative samples. Just for the higher order leakage indices, she has to look at more signatures because a smaller share of them is informative. And that's the reason why more signatures need to be looked at. Let's compare our attack results with the work of Leo et al. So again, on the x-axis, you have the leakage index, and the y-axis, the number of signatures. And you can see that for all the leakage indices, we require less signatures. And we have two improvements. So first, we discard the zero knowledge samples. And second, we reduce the error via the transformation. And this enables us to recover the secret key for all higher order leakage indices. And essentially, we process the signatures on the fly. And by that, I mean that we just need to look at this large number of signatures until we select the informative ones. We do not use all of them compared to the work of Leo et al. So, and now you have seen all these large, huge numbers, but I want to recall that after we have selected our 500,000 informative samples, the attack is really effective. Linear regression and rounding can be done in a few seconds, even for 500,000 or 2.5 million samples. And in less than a minute for any of the parameter sets, we achieve it. So let's summarize. So the new lattice signature standard MLDSA is susceptible to randomness leakage attacks. Leaking a single bit for many signatures is sufficient to recover the secret key. Our attack requires 500,000, 800,000, or 2.5 million informative samples dependent on the parameter setting. And to get this number of informative samples for every increment of the leakage index, more signatures need to be looked at, but in the end, the same number is extracted. And the attack is also, which I did not cover in this talk, but it is also applicable to noisy side channels. A bias in a bit is already sufficient for the attack. And we did also not cover module lattices, but the attack translates directly and be published already. It can be seen on ePrint, and thank you for listening. I'll be happy to take any questions.
We have 8 minutes for questions.
Thank you for the talk. Can you go back one slide? Also on this one and also on the previous one, I'm wondering, it seems that the attack is not less efficient the higher the security level of MLDSA. So are these like 4480? So I'm assuming the bigger the number, the higher the security level for MLDSA, right?
On this picture, you can see that the number of signatures that must be looked at is roughly the same for all three security levels.
Mm-hmm.
The number of informative samples that must be extracted is different. So for MLDSA 6.5, which is the middle level parameter set, MLDSA 8.7 is the highest security level, we require a different number because the beta value is different. So for MLDSA 6.5, the informative samples, they contain a bit less information, but we can take a larger share, so it cancels out, and the number of signatures is the same.
Mm-hmm. And then with the timing is also, like the middle one was so the middle one, again, because of this beta value?
Exactly, like for MLDSA 6.5, which is the middle one, we require the longest because we need 2.5 million samples to process, and that's the reason why it's the longest.
Mm-hmm. Okay.
Thank you.
I have a quick question. So what's the impact of your work on MLDSA? Do they need to change their parameters or just to use some technique against this side channel attack?
So I want to emphasize it's a side channel attack. It does of course not work if no side channel is present, but the attack applies to any Fiat Shamir with aborts signature scheme. And we did not use the many optimizations of the lithium like the module lattices. It just applies on the very basic level that we take the inner product of our secret key with some public challenge, and we add some random error. And anything that is built like this is susceptible to this kind of attack.
Okay, thank you.
Thank you.
So thanks the speaker again, and let's move on to the next paper. Yes. Yes. So the last paper of this session is titled "The Security of Hash and Site with Retry Against Superposition Attacks," presented by Haruhisa Kosaga from NTT Social Informatics Labs. Yes, please.
Yep. Thank you very much for the introduction. My name is Harisa Kosuge, and this is a joint work with Keita Kusagawa. Let's get started. This is a quick overview of our study. To understand the motivation of this work, please imagine two different words. The first word is a word with quantum universities. So quantum computers are mainly used for cryptanalysis. So ordinary people like us use classical computers. In this world, we just use EUF semi-security for securing signatures. Of course, we have to assume the quantum setting called quantum random model, but it is still EUF semi-A. On the other hand, we can consider this word. This word is the word with ubiquitous quantum computing. So everything is quantum. For example, we use smartphone with quantum power. So this is crazy, but we can consider this word. And we have to consider the security against superposition attacks in this world. It's actually impossible in the world on the left-hand side, but this is possible in this world because we can use quantum computers for signature generation. And we have two different security notions for superposition attacks. I will talk about them later. And this table is the current status of the proof of security of two major paradigms and their variants. There are two major paradigms for signature, Hashin sign and the Fiat-Shamir. And the variant of Fiat-Shamir is called Fiat-Shamir. They both are used for MLDSA. And the variant of Hashin sign is called Hashin sign with retry. And 3 out of 4 paradigms are secure in the PO and the BU security. However, we don't know yet whether the Hashin sign with retry is PO and BU secure. Actually, there is a structural difference, so we can't apply the techniques used for these schemes to this paradigm. So what we did is this. I'd like to show some definitions. The first one is the security. The EFSMA is a standard notion, and we assume the quantum mechanical model, or QROM. This red circle indicates the adversary, and the adversary has access to 2 oracles, random oracle and the signing oracle. And for the random oracle, it can make queries in quantum state, denoted by this cat notation. And there are 2 different notions for the superposition attacks. The adversary can access to the signing oracle with the quantum state. But there's a difference in the winning condition mainly. The first one is a +1, or PO security. The adversary has to submit the Q+1 pairs of message and signatures. So it must be accepted. Then after Q quantum queries to the signing oracle. So intuitively speaking, it must be hard to produce one more signature. And the other one is blind unforgeability, or BU. And in this game, the signing oracle is kind of blinded for some set of messages. Let's chapter B, sub epsilon. This is a set of messages that the adversary can't get any information of signatures for these messages. And in this game, the adversary has to submit a message and signature such that a message is in this blinded set, because he has no information about the signatures for this set. Some may think it's weird to have 2 different notions for the same purpose, but it's kind of inevitable. I'd like to show the reason using this reduction diagram. Actually, there are 2 levels of security, strong and weak. Strong security allows the adversary to win the game by forging signatures for created messages. And if we look at the relation between PO and the BU, there is no non-reduction. So we have to evaluate both PO and BU security independently. And I'd like to move on to the definition of Hashin sign with retry. This is a variant of Hashin sign. And Hashin sign is one of the major paradigms used for constructing signatures. And it uses top-down function and the hash function. And in hash and sign signature in general, we use this verification algorithm. The signature is the sort R and the preimage X. And then we compute the hash value of sort R and the message M. And we also compute F using verification key and the preimage X. And then we check if they are the same or not. If they are the same, the signature is verified as accepted. Intuitively, it must be hard to forge signature if these two functions are hard to invert. And this is a signature generation of a hash and sign with retry. We compute hash value, and this is Y. And we use trapdoor of trapdoor function to compute the preimage of Y. But sometimes it fails in the inversion. If it fails, we compute another R and compute the same thing again, and repeat this procedure until we can succeed in the inversion. And this is actually the generalization of the modified UOV and HFE signatures proposed by Sakamoto et al. And this retry structure is actually really important for building signatures. We can actually weaken the assumption for building signatures. We don't need to use PSF. PSF is a preimage sample function, and that has very good statistical property for simulating signatures. And this paradigm is adopted in several signatures. For example, UOV and QRUOV, that are the round-trip candidates for NIST PQC additional call for signatures. And I'd like to explain existing works and our research question. The hash and sign can be PO and be secure with de-randomization. The de-randomization is a technique to make signature generation deterministic by using PRF. All random values are generated by PRF. And the Fierstemeer with abort, having pretty similar structure as a hash and sign with retry, can be PO and BU secure with the de-randomization, and also we need to bound the number of loops. But we don't know yet whether we can achieve the PO and BU security in the hash and sign with retry. So this is our research question. And this is our results. The hash and sign with retry can be PO and BU secure with the de-randomization and bounding the number of loops, as in the Fierstemeer with abort. And we call this paradigm as de-randomized hash and sign with bounded retry. Sorry for long name. And this paradigm can be EF semi-secure with a good bound. Actually, we have a reduction from PO or BU to EF semi-A, but we can show better bound if we prove it from the scratch. And we have 6 reductions, and these reductions are from UF NMA. NMA stands for no message attack, and this is a kind of naive definition for signatures because the adversary has no access to the signing oracle. And we have reductions from security properties of trapdoor function to EF NMA security. So it's pretty useful. If we have this reduction, we can prove in many ways after that. And this is the randomized hash and sign with bounded retry. And there are 2 changes from the original. First, the random values are deterministically generated by PRF. There are 2 random values used for signature generation. First one is a sort for the hash function, and the other one is a random coin used for randomizing the inversion procedure. And they are generated by PRF, and the PRF takes key, message, and a counter. Because counter is needed because it must be, the random values must be different in each loop iteration. And also we have a bound on the loop numbers. And this is a proof sketch. we have to consider reduction from EFNMA to PO or BU. And this is a figure that shows the simulation of a PO or BU gain by the EFNMA adversity. And this adversity has to simulate random function, random oracle, as well as the signing oracle. And this thing is really important, really hard, because the NMA adversity has no access to the signing oracle, and also he doesn't have any information about the private key. And there are two conditions required for the simulation. The first one is simulated signatures must be verified using the random function accessed by the PO or BU adversity. I would use this notation, R sub M and X sub M. This is a simulated signature for M. And this is actually deterministic procedure, so the message M can define the signature. And to achieve this purpose, we program the random function like this equation. For the first part, if the sort equals to the 1 generated by message, if we use trapdoor function to compute the random function. And due to this equation, we can verify the simulated signature using this random function. And for the rest, we use a random function accessed by enemy adversary. Actually, this is also important for him to win this game. And we use two techniques for this purpose. And the second condition is this. The enemy adversary must win when the PO or BO adversary wins. And to achieve this, we modify the game such that this enemy adversary can win, PO or BO adversary wins only if he submits message signature satisfying the sort not equal to the sort generated by this queried message. Due to this equation, we can use the second inequality equation for the random function. So this message signature can be verified using the random function of enemy adversary. So the enemy adversary can win the game. And we use two different theorem techniques. So what is a challenging point in our proof? Actually, we followed the PO and BST proofs for the Fisher meal with the boats by Kusagawa. And however, the assumption is different. This work assumes a strong assumption on the HVZK, honest verify zero knowledge. And this is actually a strong property that can be used for simulating signatures. And we can consider the analogous assumption in the trapdoor function, but we don't want to use this one because it's too much for the Hashian sum with retried, and we don't know yet whether there is such a good property in the trapdoor function. So instead, we use this property, statistical preimage simulability. And this is a statistical indistinguishability of real generation of a preimage and the simulation of a preimage. In the real generation, we take random y, and we compute the inversion of y using trapdoor. And until it is succeeded, we repeat this procedure. And this is a challenging point. All intermediate and finite values we take in this loop iteration must be programmed as outputs of a random function. And this is a requirement of the Coulomb techniques. But if we can use a good simulability of the trapdoor function, there's no problem, but we only use the statistical preimage simulability. That permits only the simulation of the output with successful inversion, the last value of this real generation. What we did is this. We cancel the programming for failing values. To do so, we apply the O2H lemma, one-way hiding. This is a general technique used for replacing the output random function. Okay, This is the last slide. This is a security bound we achieved for the PO security as an example. Actually, the original bound is super complicated, so we simplified it. We use the notation Q. This is the sum of all queries to all oracles. And actually, this bound is tight. But however, there are some additive terms due to the usage of QROM techniques. However, we believe that these additive terms can be negligible if we set parameter appropriately. For example, if we have a large sort space, and also we have to have a negligible probability for failing to output the valid signature. Yep, that's it. Thank you for listening. Any questions?
Okay. And we have 8 minutes for questions. Yes, I think I can begin with a simple question about the motivation. Yep. So in your setting, you consider a superposition of signatures, but so you have a superposition of messages and signature. But if I want to verify the superposition, then it seems like we get something like superposition of true and false. Then how can I indicate the validity of the signature?
Yeah.
Or just because I lack the imagination of.
Yeah, it's a good question. It's verified classically, actually.
Okay.
Yeah.
So you measure the superposition and then check is true or false?
Yeah. It's measured, so it can be the classical information and verified as classical information.
Okay.
Yeah.
Okay. Thanks.
So it's not like intentionally superposition. It's a kind of the misbehavior.
Okay.
Yeah.
Yes.
Sorry, you had the table with these various assumptions. So here, these assumptions mean that you want the trapdoor one-way function to be collision resistant, or the hash function that you use collision resistant?
Yeah, this is the collision resistance of the trapdoor function.
Isn't that a strong assumption?
Yeah, strong assumption. I agree with that.
So because for multivariate, because your motivation was for MQ maps.
Yes.
And MQ maps are actually, okay, not all of them, but there are some MQ maps if they map from end to end and they're not collision resistant.
Yes, that's true. And so we need to consider weak and strong security notion. So yeah, from your standpoint, it must be really difficult to have strong security in some area of cryptography. That's true. Yeah, but if we have good trapdoor function, we can achieve it. Yep.
So can you go to the figure with the relations?
Relations. Oh yes. Okay.
This one, yes.
Yeah.
So I was just wondering, with these arrows that are slashed, is the relation unknown, or are there known separations?
Negative result.
In both directions?
Yes.
Okay, interesting.
Yep.
Okay, so that concludes this session, and let's thank all speakers again. And